Welcome to section 10.4, where we're going to be dividing radical expressions. And you recall that in section 10.3, we discussed the rules for multiplying radical expressions, wherever you had two items under one radical, or two factors multiplied together under one radical, that we could separate these into separate radicals. So if we take a look at this part here, we see we have two items, one in the numerator, one in the denominator, under the same radical. Well, just like we did in multiplication, we can divide each of the numerator and denominator under the same radical given the same nth root. So just kind of taking a look at an example of what this could look like, you could take an expression, for example, the third root of, let's just say, 100 over 4. Now, this isn't going to simplify it all. This is just an illustration of what this would look like. I can go ahead and write this as the third root of 100 divided by the third root of 4. So that would be one way in which it could be written. Another way to look at this is that we can do this in reverse also. So let's just say, for example, I have the square root of 75 divided by the square root of 3. Well, I could combine this under one large square root and make this radical 75 divided by 3. And I would be able to divide another with the radical, just like I would with anything else. And 75 divided by 3 would give me radical 25, and then that would yield the result of 5. So you see from this here, we have a new tool that we can use to work on simplifying some things. So let's begin to explore some problems taking advantage of this, and you'll find many similar ties to the work that we did in the previous section, 10.3. Let's go ahead and begin to take a look at question number 10. This is going to be the square root of 100 over the square root of 81. So now sometimes it's more beneficial to split it up into two separate radicals, and sometimes it's better to actually carry out the division. Well, this is such an example where it's going to be better to just kind of follow along here and go ahead and split this up into two separate radicals. And hopefully most of you know that the square root of 100, that's going to be 10, and then the square root of 81 is going to be 9, and that'll give us a final answer of 10 over 9. Let's take a look now at number 12, where we have a cube root. So I have the cube root of the quantity of 343 over 1,000. Well, I can go ahead and split this up now under the cube root of 343 divided by the cube root of 1,000. Well, when we do this now, the cube root of 1,000, well, hopefully most of you know that 10 times 10 times 10 is 1,000. That's fine, but not everyone may know what the cube root of 343 is. First, because this is an odd number, we know that there's going to be an odd root. So, and since it's less than 1,000, it's going to be less than 10. Well, 3 to the third is 27. That wouldn't work. 5 to the 3 is 125. So it's got to be either 7 or 9. And probably since it's pretty close to 125, yeah, it's going to be 7. So we can write our final answer to this as 7 over 10. We'll go ahead and take a look at about maybe 3 problems that are going to involve some variable expressions as well, and see how we carry these out. So, and how we go through with the simplification of these. So let's go ahead now to question number 16. Where we're going to have the square root, this is going to get big, 25a squared divided by b to the 6th. Well, I'm going to go ahead and just rewrite this as the square root of 25a to the 2nd divided by the square root of b to the 6th. So if I take the square root of 25, that's going to give me 5. The square root of a squared is going to give me a. And then the square root of b to the 6th, well, remember, you can write that as b to the 6th over 2, or you can just write that as b to the 3rd. Given the work that we did in the last section, that will make sense. So our final answer is going to be 5a over b to the 3rd. So if you look in the book here, they have this as a to the 5th. So don't worry about that. Just follow on with this example, and we'll begin to take a look at question number 18 to see what happens when we don't always lose the radical in its entirety. In question 18, we have the third root of 64 x to the 7th divided by 216 y to the 6th. So let's go ahead and see what happens in a question like this. I'm going to go ahead and I'm going to split up the top into the third root of 64 x to the 7th. And then I'm going to split up the bottom as the third root of 216 y to the 6th. So now that I have this out, I'm going to rewrite the top now as the third root of 64 times the third root of. Now x to the 7th, I want numbers that are divisible by 3. So I'm going to write this as the third root of x to the 6th times the third root of x. So x to the 6th times x is going to be x to the 7th. I want this so I can simplify this, but we're not going to be able to simplify this further. Please reflect on the work that we covered in section 10.3 for further clarification. Over here, when we have the third root of 216y to the 6th, we can write this as the third root of 216 times the third root of y to the 6th. And we don't have to break up y to the 6th because the exponent of 6 is evenly divisible by 3. So now I'm hoping to get away from having to rewrite all of these out, showing the fractions, but I'll use it for this one. So the cube root of 64, that's equal to 4. I can write this as times x to the 6th divided by 3. And here, this is not going to be evenly divisible, so I'm just going to keep this as the cube root of x. The bottom here, the cube root of 216 is going to be 6. Then I have the cube root of y to the 6th. Well, I'm going to write that as y to the 6th over 3. So when I simplify this a little further, well, 4 divided by 6, I can reduce that to 2 over 3. I have y to the 6 over 3, or x to the 6 over 3. That's going to be x squared times the cube root of x. At the bottom, y to the 6 divided by 3 is going to be y squared. And that is as simple as I can get the answer to question 18. Let's go ahead and take a look at question 20 now. This is going to be the fourth root of 81 x to the 4th over y to the 8th z to the 4th. Okay? So I will break it up into these different radicals, but I probably will skip this step, hoping that this is going to be easier to you. If you have difficulty seeing the math without that step, though, please feel free to ask me in class. So now I'm going to split up the top and bottom, so I'm going to write this as the fourth root of 81 x to the 4th divided by the fourth root of y to the 8th z to the 4th. Well, what I can do at this point now is I can split up the top. And yes, 81 is a perfect fourth. The fourth root of 81 is equal to 3. Okay, so what I would do on the top of this now, fourth root of 81 is 3. Fourth root of x to the 4th, well, 4 divided by 4 is 1, so that'll be just x. 8 divided by 4 is going to be y to the 2nd. 4 divided by 4 is going to give me z. And now I have my final simplified answer for question 40 as 3x divided by y squared z. Let's check out one more of these types of questions and let's see exactly where this is going to take us. So we're going now to question 24 and let's see what happens with that. So this is going to be the fifth root now. Notice these are just getting bigger, but same rules apply. Fifth root of 243 times a to the 9th divided by b to the 13th. So what I'm going to do first, I'm going to go ahead and split up the top. And I'm going to split up the bottom, get my fifth roots down each of 243 times a to the 9th. And this will be the fifth root of b to the 13th. So I'm going to split up the top now as the fifth root of 243 times the fifth root of a to the 9th. Now, if you're comfortable skipping this step, you don't have to do this extra work. Just like I skipped the step of writing it as a rational exponent. But if you want to continue to do that work, you're welcome to do it also. So I'm going to just keep the bottom as it is, as the fifth root of, well, now I'm going to make a slight change here. And I'm going to make a slight change to this one also. So I can, let me keep it like this. B to the 13th. Well, I want to be able to split this up a little further, so I can take a to the 9th, is write it as a to the 5th times the 5th root of a to the 4th. So I'm going to make that the 5th root of 243 times the 5th root of a to the 5th times the 5th root of a to the 4th. B to the 13th, well, I can split it up and make it b to the 10th times the 5th root of b to the 3rd. We want the largest exponent as possible here that's evenly divisible by 5. And we have that here. So this will simplify, this will simplify, and this will simplify. Something you may not know offhand, but remember 243 is odd. And it's to the 5th exponent, so we expect this to be a low number, and in fact it turns out that 3 to the 5th is 243. Therefore the 5th root of 243 is 3. So that will be 3. The a to the 5th root of a to the 5th is a, and then that will leave us with the 5th root of a to the 4th. In the denominator here we have the 5th root of b to the 10th. Well, 10 divided by 5 is 2, so we have b squared times the 5th root of b to the 3rd. So this would be times the 5th root of b to the 3rd. And we have this for our final answer in question 24. So in this case here, with these problems that we've done, we've split it up where we put a radical in the top, a radical in the bottom, taking advantage of the property that we learned about at the beginning of the lesson, and then working to try to simplify each piece as much as we can. We're now going to take a look at where these are separated and where there might be situations in which it may be helpful to combine the radicals together to simplify. There is no magic formula to follow for this. It's just a question of getting more comfortable with the math to know when this is appropriate. So let's take a look at 28 to further clarify what I'm talking about. So this is going to be the square root of 700x divided by the square root of 7x. So what I'm going to go ahead and do is I'm going to put this under one radical, carry out the division, and let's see what I get. So if I put this under one radical, I'm going to get 700x divided by 7x. Well, 700 divided by 7, that's going to equal 100. And x divided by x, that will reduce. And as we know, the square root of 100 is equal to 10. So by using this technique, we kind of get a shortcut to be able to get to an answer much faster that would have been difficult to do without. Now, this doesn't always work, and sometimes the radical is just going to remain. Let's go ahead and take a look at question 30. Here we have the cube root of 35 divided by the cube root of 5. So I'm going to go ahead and combine this in one radical as a cube root of 35 divided by 5. And, well, when I get done with this, all I'm going to have is 35 divided by 5 is a cube root of 7. And you'll probably figure out pretty quick that there's not a whole lot we can do with that, so we're just going to go ahead and leave it as the cube root of 7. And that's a perfectly acceptable answer. It's just something that is not further simplifiable. So let's begin to look at some of the problems and see how this extends through. Let's take a look now at 34. So in 34 we have the cube root of 189, x to the 5th and y to the 7th, divided by the cube root of 7x squared y squared. So we're going to use a few rules here. First, we're going to combine these under one large radical. So it's going to be the cube root of the quantity of 189 x to the 5th y to the 7th divided by 7 x to the 2nd y to the 2nd. So first thing we need to figure out is, what is 189 divided by 7? Well, that's going to turn out to be 27. Next, x to the 5th divided by x to the 2. We know from lesson 10.3 that this is going to be x to the 5 minus 2, or x to the 3rd. So where are we getting this from? We're going to first take 189 divided by 7. That's going to equal 27. We know that for x to the 5 over x to the 2, this is equal to x to the 5 minus 2, and that's x to the 3rd. And then finally, for y to the 7th over y to the 2nd, this is equal to y to the 7 minus 2, or y to the fifth. So we're going to go ahead and put that here now. So now we have the cube root of 27x to the third y to the fifth. Some of this will simplify nicely, some of it won't. Well, we can take the cube root of 27 and get 3. That's not hard. X to the third is also divisible by 3, so I can simply write this as the cube root of x to the third. But now y to the fifth is not evenly divisible by 3, so I'm going to need to split this up into y to the third times y to the second under two separate cube roots. This, and this will simplify. This won't, so we know the cube root of y squared is going to remain behind. The cube root of 27, that's going to be equal to 3. The cube root of x to the third is going to be x. The cube root of y to the third is going to be y. So it's going to be 3xy times the cube root of y squared. And that's going to be our answer to question 34. We're going to take a look at one more mega question in this way and see what this looks like. Actually, two more in this area. So first we're going to take a look at questions 38. And then we're going to take a look at question 40, which will be just a little more sophisticated in its application. 38 is going to be the fifth root now of 64a to the 11th b to the 28th divided by the fifth root of 2ab to the negative 2. Okay? So quite a bit going on here, but don't let the size of the number scare you. There are rules for this. So let's just first get this under one large radical. So this is going to be the fifth root of 64 a to the 11th b to the 28th divided by 2a b to the negative 2. Okay, so let's see if we can make this, get rid of the denominator by dividing this out. We know that 64 divided by 2 is going to equal 32. That's fine. We know we have a to the 11th divided by a, so that's going to be a to the 11 minus 1. That's going to be a to the 10th. That's fine. And be careful of this one here. We have b to the 28th minus, what are we subtracting? Negative 2. Now, if you want to move this to the top, the result will still be the same, but it's going to give me b to the 30th. So right now, I have these three things that I figured out. So this is going to be equal to the fifth root of 32, a to the 10th, b to the 30th. Fortunately, everything is a perfect fifth root. I'm going to skip the step of even separating these out because everything is kind of nicely done here. The fifth root of 32, that's equal to 2. A to the 10th, 10 divided by 5 is going to be a to the second. B to the 30th, 30th divided by 5 is equal to b to the 6th. So this is going to be the final answer to simplify this monster of a radical fraction to the fifth root. Here's our final answer to question 38. Let's take a look at question 40. 40 has a little bit of a different look to it. Here we have the third root of r to the third plus s to the third. This is going to be divided by the third root of r plus s. So some of you may look at this and wonder how we would ever tackle this. Well, first, what we're going to go ahead and do with this is let's just go ahead and put this under one radical, like we talked about. We have r to the third plus s to the third over r plus s. What we're going to do with this now is, you should recognize that r to the third plus s to the third, this is the sum of perfect cubes. And we can factor the sum of perfect cubes. And when we factor the sum of perfect cubes, you should find the formula to be r plus s times r squared minus rs plus s squared. After that, we're going to write this divided by r plus s. So now what we can do is we can kind of carry out the division. And then the best we can do with this question is we can now write this as the third root of r squared minus rs plus s squared. At this point, there's not a whole lot we can do with this expression any further. We just need to leave it as is. But here is a technique where sometimes factoring may be involved, in the simplification process. So this is how we go back and forth with this. This is the first part of the lesson. We're going to go ahead and pick up with the second part of the lesson here now. So there's a phrase you're going to be learning about, and that I'll be using in class, called rationalizing the denominator. So any number that remains under a radical that we can simplify such that we can take the radical away to express it. This is a number that we consider irrational. So when we talk about rationalizing the denominator, what we're talking about is to remove needing a radical from the denominator. So when we talk about removing a radical from the denominator, let's see what this practice is going to look like. We're going to start with a fairly simple question to begin with here. Let's go with 42. I'm going to start with radical 6 over 7. And I'm going to rewrite this so that I have radical 6 over radical 7. So it looks like when I first look at this, there's nothing I can really do within the question itself to simplify this. But one thing that I can do is I can multiply the denominator here by radical 7. But if I multiply the bottom by radical 7, I need to multiply the top by radical 7 as well. When I do so, radical 7 times radical 7 is going to give me 7. Radical 6 times radical 7, that's going to give me radical 42. Now, there's still a radical in the numerator, but that's okay. By multiplying the top and bottom by radical 7, I've now made the bottom a whole number or a whole expression, therefore rationalizing the denominator. We'll take a look at a few more fairly straightforward examples to see how this principle works. Let's go ahead back to 41. I have radical 3 here over 2, so radical 3 over 2. I can write this as radical 3 over radical 2. So I see there's a radical 2 down here. I want to get rid of the radical. So I'm going to go ahead and multiply the bottom by radical 2 and the top by radical 2 because I don't want to change the value. It's kind of like when you want to be able to add and subtract fractions with common denominators. We need to multiply the top and bottom by the same thing. Well, here, we don't want to change the value of the fractions. And we just want to make sure we don't need a radical below to express it. So if I take radical 2 times radical 2, that would give me radical 4, just 2. And then radical 3 times radical 2 would be radical 6. And that is how I rewrite this fraction so that the denominator is rational. I rewrite this fraction so that the denominator is rational. Let's take a look at a few of the problems. Not so difficult, but just reinforce this concept. Here we have 3 radical 5 divided by 2 radical 2. Well, there's no problem with having a radical 2 below here, or having a 2 below here, but the radical 2 is an issue. So since we have a radical 2 here, we want to get rid of that. So I'm going to multiply the top and bottom by the radical 2. So as I carry out this multiplication now, I'm going to have radical 5 times radical 2. That's going to be radical 10. So this will be 3 radical 10. And then here we have 2. Radical 2 times radical 2 is 2. So that's going to give me 3 radical 10 over 4. And that is as simple as I can express that fraction. Sometimes what may happen after this work is you may have further simplification either under the radical or within the new formed fraction itself. Just have to be something you look out for. Let's go ahead and take a look at another such problem where this process can get let's look at just a few more simple ones like this to kind of reinforce this process with the square root. So 56. Here I have 7, the square root of 7 over 32 e to the second b. So what I need to do is I'm going to go ahead and I'm going to split this up now. I'm going to make this the square root of 7 over the square root of 32 e to the second b. So if I have the square root of 7, if I have the square root of 32, the square root of a squared, square root of b. Well, 32, that's not quite a perfect square, so I can rewrite, I have to do a little rewriting down here. So I can write the bottom as the square root of 16 times the square root of 2 times the square root of a second times the square root of b. Keep the radical 7 on top. Well, the square root of 16, that's equal to 4. The square root of a squared is equal to a. Then I have the square root of 2 and the square root of b, so it's going to be the square root of 2b over the square root of 7. So I have the square root of 7 divided by 4a, the square root of 2b. So I realize now that, well, I simplify this quite a bit, but I need to get rid of that 2b, so I'm going to multiply the top and bottom now by 2b, the square root of 2b, that is. On the top, I'm now going to get the square root of 14b. On the bottom, I'm going to have 4a. Well, the square root of 2b times the square root of 2b is just going to be 2b. And now I'll have the square root of 14b divided by 8ab. And that is the final answer to that in simplified form. So we have these with square roots, but we can also do this with other types of roots as well. Just have to be careful, and for this we're going to use fractional exponents. So let's take a bit of a look at that. So we're going to look now beginning at question number 48. Here we have the cube root of 7x divided by the cube root of 3y. Okay, so one thing that we can do to simplify this question a little further is I'm going to go ahead and I'm going to write the bottom now. In fact, I'll write the top this way also. I'm going to write this as 7x to the 1 over 3. But now I'm going to write 3y to the 1/3. So here's where this begins to get a little confusing. Because what I'm going to do now is I'm going to write, I need to get rid of the root. I need to make this an exponent of 1. So I'm going to multiply at the bottom by 3y, not to the 1/3. That would only give me 2/3. But I'm going to multiply by 3y to the 2 over 3. Because when I multiply these together, 1/3 plus 2/3 is going to equal 1. So on the bottom, that's going to give me just 3y. But when I multiply this through on the top, 3y to the 2/3, that is going to look a little different now. So one way that we can make sure that these kind of have the same expression is we can take now this 3y to the 2/3, and we're going to write it in the following way. So we can take the 3y to the 2 over 3, and instead of doing what we did in the last section, we're going to write it as 3y. Let me put this here because that's a proper way to write it. I'm going to write this as 2 over 1 times 1 over 3. So what I need to do is I need to take the quantity of 3y and square it. So if I take the 3 and I square it, I get 9. If I take y and square it, I get y squared. And now I take 3y and I square it to get 9y squared. I'm going to raise that to the 1/3. It's important if I'm going to take this quantity here. So I'm going to rewrite this expression again. I need to have this and this have the same exponent if I'm going to multiply them together. So now I'm going to have 7x to the 1/3 times 9y squared to the 1/3. And now I can get a new product that's going to be raised to the 1/3. 7 times 9, 63 x y squared. And this is all going to be what? To the 1/3. Which I can now express going up here as the cube root of 63xy squared. So what I'm doing now is I'm just taking this as a fractional exponent or rational exponent and putting it now in radical form. Yes, this part is tricky. I'll be sure to go over a couple more examples with you to further clarify this process before we wrap up the lesson. But this is confusing the first time you see it. Please use MyMathLab and the tools there kind of help you through this process and keep viewing this lesson. Let's go ahead and take a look at number 50 now. This is going to be the fifth root of 3a to the fourth divided by the fifth root of 2b to the seventh. So I'm going to go ahead and, well, we don't worry about what's at the top here so much. What I'm going to do when I write this here, since I have the fifth root here, is I'm going to just write this out a little bit. I'm going to write this as 3a to the fourth to the 1/5 over the quantity of 2b to the seventh to the 1/5. So when I split this up, it's going to get a little messy. So I have this to the 1/5. I want this to be 5 over 5. So I'm going to need to multiply the top and the bottom. Well, if this is 1 over 5, I need to multiply the top and bottom by 2b to the seventh. Now, there will be some cleaning up that's going to need to be done here, but I don't recommend trying to simplify this first. So this will be 2b to the seventh to the 4/5. So I'm going to multiply the top by 2b to the seventh to the 4/5. So we're going to have a little work to do up here, because in order to multiply these numbers together, I need to have the same exponent with them. So on the bottom, because I have 2b to the seventh to the 1/5 times 2b to the seventh to the 4/5, I'm going to have 2b to the seventh to the 5/5, or just 1. What is the top going to look like here? So let's go ahead and just write out this work here. 3a to the fourth to the 1/5 times 2b to the seventh to the 4/5. I want to get this to have an exponent of 1/5 so I can multiply what's inside these. So I'm going to write out 2b to the seventh, and instead of 4 over 5, now I'm going to write it as 4 over 1 times 1 over 5. So 2b to the seventh, that's going to be times to the fourth. Well, 2 to the fourth is going to be 16. B to the seventh to the fourth, I multiply these together. That's going to be b to the 28th, and that's going to be divide that, or raise that to the 1/5 exponent. So now I have these together here. I now have this raised to the 1/5. I'm going to put this back into here. So now this is going to give me 16b to the 28th raised to the 1/5, and that's going to be times 3a to the 4th raised to the 1/5. So what I'm going to have on the top now is 3 times 16. That's going to be 48. A to the 4th, well, these can't be multiplied together, so I'm just going to a to the 4th times b to the 28th, and this is all going to be raised to the 1/5. What am I going to have left on the bottom? I'm going to have 2b to the 7th. Now, is there some simplifying that can take place here? Yes, there is. So we're going to take a look at how we can further simplify that, and let's see what we can do with that. Well, there's no fifth root of 48, and in fact there's no number that will factor out, so 48 is going to remain under the radical for this one. A to the 4th we can't do a whole lot with, but b to the 28th we can. So if we wrote out 48 to the 1/5, nothing much we could do with that. If we have a to the 4 over 5, well, can't do much with that. But now b, let's go ahead and b to the 28 over 5. Well, one way I can write out b to the 28 over 5, and I can write this out as b to the 25 over 5 times b to the 3 over 5. So this one's actually going to pull out. So we'll be able to write that as b to the 5th times 48 times a to the 4th times b to the 3rd, all to the 1/5. And that's going to be over 2b to the 7th. And if you notice, yes, you have b to the 5th here, b to the 7th. So the final way we would write this, if I divide both of these out and have b to the 2nd left here, is we would have the 5th root of 48, a to the 4th, b to the 3rd, all divided by 2b squared. This question is really complicated. And if you have a slight headache after trying to work through the technicalities of that question, or if you feel like that is just too beyond you, I recommend don't beating yourself to death about it. You'll probably see one question up for a test about it. Try it once for a homework. That's only the only thing I'm expecting. Don't kill yourself, and don't worry if you don't understand this question too well. This is complicated. For those that can get it, great. If you can't, not the end of the world. But I wanted to show how this is done. And please bring your questions to class on it if you have any. Thank you.